In order to understand what gives rise to different signals in an NMR spectrum, we need to take a look at chemically equivalent versus chemically distinct hydrogen. And what we're going to see is that protons that exist in sort of a different environment, they're going to give different NMR signals. But protons that exist in an identical chemical environment, they're all equivalent and they're going to correspond to the same signal. So first, if we look at methane, there's 4 hydrogen around this carbon, but all 4 of these are completely identical. So these are 4 chemically equivalent hydrogen. Since they're all chemically equivalent, methane, which is this compound, is only going to have 1 signal in the NMR. And that 1 signal is going to correspond to 4 hydrogen. Now if we look at ethanol, we have a hydrogen on an oxygen. We have this CH2 and a CH3. Well, these 3 hydrogen on this carbon on the right, all 3 of those are chemically equivalent. They're all on this methyl carbon. So we'll call that signal A. Then we have this CH2. Now these 2 hydrogen, they're equivalent to one another, but they're on a CH2. They're different than these hydrogen on the methyl. They're different than the hydrogen on the oxygen. You would never get this confused and say that one of these hydrogens were the ones on the oxygen or on the methyl group. You can always distinguish these 2 as their own separate type of hydrogen. So we'll call that type B, and then the OH hydrogen is type C. So there are 3 different types of hydrogen in this molecule. So 3 distinct types of hydrogen, 3 signals. We'll have 1 signal that corresponds to 3 hydrogen, 1 signal that corresponds to 2 hydrogen, and 1 signal that corresponds to the 1 alcohol hydrogen. Looking at a couple other examples here. Here we have an ether. Now a common misconception is for people to say, well, here's a methyl group, here's a methyl group. Well, those are the same, but they're not. They're chemically distinct methyl groups. Now all 3 hydrogen on this first methyl group, all 3 of these are the same, and that's one type. We'll call those A. But this methyl group's directly attached to an oxygen. The methyl group on the right isn't. So there's no reason to have any confusion between the methyl on the right and the methyl on the left, because they're in different chemical environments. They're in different spatial relationships. So they're different. Now the 2 hydrogen on this carbon, they're equivalent, so that's type B. And then of course in this other methyl group, these 3 hydrogen are all equivalent, that's type C. So we're going to have 3 different signals in the NMR for this compound. Okay, now this next example is just a little bit more complex in that we have to take account of the fact that there is free rotation around single bonds and there is symmetry here. Remember, we have free rotation around this single bond, so we can draw a conformation, and we'll keep the left-hand side the same. If we rotate it around this single bond, we can rotate this other methyl group up, and you should be able to see that there's a plane of symmetry that runs through this compound. So that means that these 2 methyl groups are equivalent, these 2 CH2 groups are equivalent. So there's no way to distinguish this methyl group on the left from this methyl group on the right, because if you flip it over, how can you tell the difference? That should be A. So both of these methyl groups are chemically equivalent. Now the CH2 group is certainly different than the methyl group, so that's our second type of proton, but the CH2 on the left is the same as the CH2 on the right. So this has two distinct types of hydrogens. We're going to see two signals. One signal is going to correspond to a total of 6 hydrogen. The other signal is going to correspond to a total of 4 hydrogen. I guess that would be A and B. Okay, now we'll look at a couple that have carbonyl compounds in their structure. Now keep in mind, on this carbonyl compound, this carbon has no hydrogen, so you're not going to see any signal for that. But here we have a methyl group. All 3 hydrogens in the methyl are equivalent, so that's one type. We have a CH2 group, that's our second type. And now we have another methyl group, but it's not equivalent to the methyl on the right. This methyl on the right is directly connected to a carbonyl. The methyl on the left is separated by a CH2 group, so these are distinct. So that's type C. So 3 signals, or 3 distinct types of hydrogen. This next one, we have an NH2. Well, the hydrogen on that nitrogen are one type. We have a CH2, that's a second type of hydrogen. We have this hydrogen on this tertiary carbon, the CH. Okay, that's a different type. But now these 2 methyl groups in this isopropyl, they are equivalent. So these 3 protons on this methyl group and the 3 protons on this bottom methyl group are 100% equivalent. Remember, you have rotation around that bond, so there's no differentiation between those. So this has 4 distinct types of hydrogen. And there's 4 signals in the proton NMR. Here's an example involving an alkene. Now remember, when dealing with alkenes, this alkene locks that bond in place. There's no rotation. So if we look at these different protons, well, we have our methyl group. The methyl group's certainly different than these protons on the alkene. So we'll make that A. Now we have this alkene proton that we'll call B. It's on the same carbon as the methyl. It's different than these other 2 alkene protons because they're 1 carbon removed from the methyl. So now, since these 2 are different than this alkene proton, we'll label this one as C. And proton C is and always will be cis to the methyl. But this proton on the bottom, we're going to label that as D because it's trans to the methyl. And it always will be. So protons C and D are chemically distinct even though they're on the same carbon atom. And that's because we're locked by this alkene. So this is going to have 4 signals. Now by comparison, if we had something that made that alkene symmetrical, let's say 2 chlorines, now both of these protons are in an identical chemical environment. This proton on top is cis to one chlorine, trans to another. Proton on the bottom is cis to one chlorine, trans to another. So these two protons are chemically equivalent. And this compound would show one signal. Now it becomes slightly more tricky when dealing with a ring. And I think for rings it really helps to sort of try to draw the ring in a somewhat flat perspective and then put your substituents pointing directly up or down. So I'm going to draw this cyclopropane on top. And then I have chlorine up, hydrogen down, another chlorine up, hydrogen down, hydrogen up, hydrogen down. Now by looking at this, you can see that there is a plane of symmetry that runs through this compound. So that means whatever is on the left is projected on the right. So these two protons on the carbon bearing the chlorine on the left and right, they're equivalent. Now these two protons on this carbon of the cyclopropyl, of the cyclopropane, they're different than proton type A. But now this proton on top is on the same side as chlorine. This proton on the bottom is on the opposite side of the chlorine. These two protons see different things, they're in different chemical environments, so they are chemically distinct. So we'll call this one on the bottom B, this one on the top C. So there will be 3 signals. Now let's look at this trans dichlorocyclopropane. Let's go ahead and draw our chlorine or our cyclopropane in the same perspective. We have a chlorine up and a chlorine down. Now, if we look at this one, we have this proton, and think about what it sees. Well, directly across from it is a chlorine. Attached to the same carbon is a chlorine, but it has a cis chlorine on this side. But now if we compare that to this hydrogen, on its carbon it has a chlorine attached, and it also has a cis chlorine. So these two hydrogens are in fact chemically equivalent. Now these two hydrogens, if we think about them, the hydrogen pointing up, it has one cis chlorine, one trans chlorine. The hydrogen on the bottom also has one cis chlorine, one trans chlorine. So these two hydrogen are also chemically equivalent. So this would be B, and this one is B. But they are distinct from the two hydrogens on the carbons directly attached to a chlorine. So this would give 2 signals. Now we're going to sort of build on what we've been talking about and look at the difference between what are called enantiotopic protons and diastereotopic protons. And to help us figure this out, we're going to use a chemical equivalence test, or something I like to call the X test. And if two protons are in question, what we're going to do is we're going to draw our compound twice. And those two protons that are in question, in one of our drawings, we're going to replace one of the hydrogen with an X. In our second drawing, we're going to replace the other hydrogen with an X. Then we're going to figure out the relationship between those two compounds. If the two are identical, then those protons are identical and of course chemically equivalent. If the two compounds are enantiomers, those protons that we're looking at are said to be enantiotopic, but they are still chemically equivalent and result in the same NMR signal. And finally, if the two compounds are diastereomers, those protons are considered diastereotopic, and they're not equivalent, and they will give two different NMR signals. First, we'll look at one that has identical protons. And although I've highlighted all three protons on the methyl group of butane, let's actually just compare these two with the dash and the wedge. So I'm going to draw this compound twice. And in one, I'm going to replace one of my hydrogen in question with an X. And then in my second, I'm going to replace the other hydrogen in question with an X. So if we look at these compounds, although we're showing three-dimensionality at these carbons, they're not chiral centers because there's not four different groups around that carbon. Additionally, if I rotate around the carbon bond of one of these, I'm going to rotate this and put X pointing out, this hydrogen into the plane, and this hydrogen is now in the plane to the back. Well, what I have here are two identical compounds. So these two hydrogen are identical, and of course all three of these in the methyl group, like we've seen before, will give us one signal. Now let's look at the CH2 group on butane. So we're looking at these two hydrogens. Let's draw two representations and replace the hydrogen of each with an X. First one, I'll do the one pointing out as a hydrogen, the one back as an X. The second one, I'll do the one pointing out as the X, the one back as a hydrogen. Oh, I drew too many carbons. Alright, now, if we look at the carbons in each of these, now we have four different groups around this carbon that is a chiral center. We have an ethyl, methyl, hydrogen, and X. Now, what are the relationships between these two compounds? Well, they're non-superimposable mirror images, so these two are enantiomers. So what does that mean? That means that these two hydrogen are enantiotopic. But even though they're enantiotopic, they do produce the same NMR signal. So they are chemically equivalent, and these two hydrogens still only correspond to one NMR signal. Finally, let's look at a case where we have diastereotopic protons. And the change here is I've installed a chlorine and I have a chiral center here. And although I've shown the stereochemistry of this chlorine, even if I had left this as just a regular line and not shown it as a wedge, it would still be a chiral center and would have an effect on these protons. But let's draw this twice. Chlorine out, I'll do a hydrogen out, and now pointing back the X, and then I'll draw the second representation. I still have the chlorine out, but on this one I'll put the X pointed out and the hydrogen back. Now I have two chiral centers. One stays the same between the two, one changes between the two. So these two compounds, they're non-superimposable, they're not mirror images, so they're diastereomers. So that means these two protons are diastereotopic. And these are each chemically distinct. And if we were to look at the proton NMR spectrum from this, our methyl group would be type A. These two are distinct, so signals B and C. We also have a hydrogen here, which would be D, and then this methyl group would be E. So this compound would have 5 signals. All right, one final example to look at. We have this cyclopentanol, and we want to figure out sort of the relationships between all the hydrogens and how many different signals we're going to have. So let's draw this and sort of put in all of our hydrogen. And we're going to give it three-dimensionality. So although the OH is already shown pointed out, let's draw in a hydrogen back, and then on every carbon, let's do a hydrogen out, hydrogen back. Now we won't go through and do that X test with this one, but you certainly could. Alright, so let's go through and kind of see what we have here. Well, the first thing to take note of is the fact that there is a plane of symmetry that runs through this compound. So everything on the left is mirrored on the right. But our alcohol, OH, that's one type of proton. Then this carbon here, we have this hydrogen, that's a second type. Now we have these two hydrogens pointed out, but they're mirrored. So they are chemically equivalent. And we'll label that one as C, this one as C. But the hydrogen pointed back is distinct from hydrogen C. And one way to think about this hydrogen pointed out is pointed up in the same direction as the OH. But the hydrogen pointed back is in an opposite direction of the OH. So these two hydrogens see different things, they're in different chemical environments, so they're different. Now we come down to this next carbon. We have on the left and right hydrogen pointed out, which are equivalent. Let's label those as E, and the hydrogen pointed back, which are different because they're opposite this OH, so they're type F. So this particular compound is going to have 6 signals. Now, if you want to think about the types of relationships, especially between some of these protons on the ring, so protons C and D, if you were to replace those with an X, you would see that you formed a pair of diastereomers, so they're diastereotopic. Same thing for E and F, they're diastereotopic. Now, if you wanted to compare proton types, let's just do E for example, and you did the replacement test, you would find that these two would give rise to a pair of enantiomers. So E and E are enantiotopic, hydrogens F are enantiotopic, hydrogen C and hydrogens D are pairs of enantiotopic protons.